Go for it.
Molecular modeling in medical research by yours truly. Alright, so you must be wondering, what is molecular modeling and why the hell should we care? So, by definition, it's a technique for deriving, representing, and manipulating the structures and reactions of molecules. These models are created by mathematical equations that calculate energy that puts calculated by energy that's put into a molecule or a reaction, basically. And also, just as a side note, they can also be hand-drawn. An example of molecular modeling, Dr. Agbo used it in his research. Which one, I'm not exactly sure, but he used one. So here's some examples. Like I said, they can be hand-drawn. The common ones are Lewis and Vesper models. They're really good for beginners who's just learning about Gem Chem, but they do have limitations. For instance, Lewis cannot determine an actual bond angles and bond lengths of a molecule, and Vesper fails to predict the shapes of the transition metal compounds and those with heavier main group elements. So to make a more accurate representation of these molecules, they created, scientists have created 3D molecules, or models rather. And some examples are molecular mechanics model, quantum chemical model, and semi-empirical. And here are just different examples of one of each of those models. So this is the molecular mechanics model. It basically shows molecules in terms of bonded atoms. This model focuses on the geometrical parameters from one molecule to another and the mixing of atomic orbitals to accurately estimate bond lengths and angles. So basically it regards molecules as being masses, which are the atoms, and as springs, which are the bonds, and to preferred lengths and angles. It really regards it as a mechanical equation more than just like chemical characteristics, hence its name, molecular mechanics model. It's a really great tool, and here's some of the examples. It's one of the equations to create, calculate bonds in a molecule, angles in a molecule, and the torsions, which are where if a molecule has a really strong attraction, it like moves around and twists. It won't break, but it's just a lot of movement. So it has limitations. It can't do. It doesn't regard electrons in a molecule, and it can't show ionization energies and other electron characteristics. It can't explore the processes of bond breaking and making. It can't evaluate energy of transition states and activation energies in which reaction rates can be derived. And it cannot calculate the heat of formation and combustion. So here's a couple examples of molecular modeling, spoken ball, and space filling. Next is the quantum chemical model. It's also called ab initio model, which means from the beginning. It's based off of theoretical principles, and it's heavily based on the Schrödinger equation, which is right here. I don't know a whole lot about this, and for those taking physical chemistry, God help you. I don't understand any of this hardly, other than this is that Hamilton equation, which is a scalar value of the Schrödinger equation, and this equation involves polar coordinates to create these models. Now, basically just calculates the locations of atomic nuclei and all the electrons. It really exceeds all the limitations of molecular mechanics models, but it takes forever to do because it's going through the energies for every electron in an atom and then in the molecule. So in other words, nobody has time for it. Then we have the semi-empirical model, which can be used for both molecular mechanics and quantum chemical model. It basically is a compromise between speed and accuracy. It basically makes the molecular mechanics model more accurate and less time consuming. Like it takes into account of the valence electrons in the molecule, but not everyone, making it more accurate and less time consuming. And here we just have an example, which is a 3D electron density model and a lowest unoccupied molecular orbital model. So try not to take too much of your time. I'm going to show 3 applied cases of which they use molecular modeling in medical research. They used it in using organic electron ion pumps, research in studying DNA, and neuro studies. So what are organic electron ion pumps? They're commonly used tools in the medical field. They're basically electrophoric drug delivery devices that oncologists use to treat patients with pain medication. It looks like a normal needle used for IV, but it applies electricity to give precise amounts of a certain drug. Like it's more precise and it gives a specific amount than just a normal needle. And here's like a physical diagram or theoretical diagram of like what is actually inside of that needle, so to speak. Basically this here is like a membrane in which the substance goes through, because the substance is either too small to look into a microscope and it can't or they're too big to pass through normal membranes. So they specifically made this to compromise between them. So here's one example where a couple researchers went beyond the normal uses of OEPs, organic electron ion pumps, and it can also be used for neurotransmitters, to study neurotransmitters. And in this, they used a common one, GABA, which is the chemical that's released at the end of nerve cells. And what they hypothesized that these tools have an effect, are affected by pH and their transfer of, or their transportation of different substances. So, and neurotransmitters, they're heavily affected by pH. So they used, they changed the pH when this was delivered. So they found that at pH of 3, the GABA molecule was at a highest efficiency at transporting or passing through that tool, because it had a shorter radii gyration, which basically is saying that carbon with nitrogen atom isn't moving around as much as compared to the other where there's at different pHs. So it allowed it to move faster because you didn't have as many the GABA molecules colliding with each other. So here they used a molecular mechanics model because it's just showing the dynamics of it and the movement of the molecule. It isn't really taking account into the electrons or ionization energies, just showing the movement. Now for DNA studies, this is a very useful tool in studying basically the molecules that are within DNA strands, just to summarize all of what this is saying. And this study Researchers were looking into using quadruplex aptamers in DNA. Just to summarize, these structures can cause cancer, or the reason cancer forms in cells. So they were trying to look into it and understand how these things form and why these occur. So in this experiment, they basically labeled a TBA aptamer, which was a T9, into a quadruplex and used fluorine-19 NMR spectroscopy to basically get a visual of where this structure right here would bind to, in which they found it was like at the top of this formation. And here they also used a molecular mechanics model because they didn't really focus into the electrons or the kinetic energies. It's just simply where this was binding to when they, this is based off of the readings from spectroscopy and showing the distance between fluorine and the TBA or T9 nucleotide. Then one last example, neurostudies. Like DNA, they were looking into it on a molecular scale for studying the brain. Like here, they looked into molecules that are binding into brain cells that pass through the brain-blood barrier. So in this study, well, first off, when people are transferring drugs to basically kill tumors in the brain, they have this huge obstacle, and it's the brain-blood barrier, because there are certain enzymes in it, like GSTs, which are glutathione S transferases, I think. They basically metabolize anti-tumor drugs, and the drugs, they are useless after this. So, not sure what 8-MOP has been used before, but it's an inhibitor that they used to suppress the activity of GST, in which GSTP1 is the most common one found in the brain-blood barrier. And they compared it to another inhibitor, which is NBDHEX, and they found that this inhibitor had proven to have anti-tumor effects and stop and decrease the rate of GSTP1 activity. Here they used semi-empirical because it's a bit of both quantum mechanics models and molecular mechanics models, because it's talking about finding kinetics and finding energies needed for these inhibitors to attach to the enzymes in the brain-blood barrier, and just to basically show, but not showing like the entire, again, not the entire electrons that are in this. Then they also just showed like a Lewis and Vesper model as well. So my conclusions is that they've proven to be useful in these different applied cases in medical research. And do you guys have any questions?
Yay! Clapping. Any questions? Oh, sir. All right. You guys can get me your things. Thank you, sir. Let's see, Malik. Somewhere, that's not it. This is not it.
Yeah, I can.
Lucas. Once I